You plug in a brand new 65-watt charger, expecting lightning-fast speeds. But if you were to measure the actual power flowing through the cable, you'd see something strange. Your phone is pulling significantly less than 65 watts. We tend to imagine chargers as simple pipes. The assumption is that if you buy a 65-watt brick, it opens a valve and pumps 65 watts of continuous electricity straight into your phone's battery until it's full. To understand why that doesn't happen, we have to look at how electrical power is defined. Power equals voltage multiplied by current. When you multiply the voltage, the electrical pressure, by the current, which is the actual flow rate of the electrons, you get the total volume of power. That 65-watt label printed on the side of your charging brick represents the absolute maximum capability of the internal components under perfect laboratory conditions. It is not a guaranteed constant output. The modern charging brick is a highly active power conversion system. It requires a continuous digital handshake with your phone in order to operate. That bold number on the box is a theoretical ceiling for a complex, real-time negotiation. This negotiation starts the moment power leaves your wall outlet and enters the physical circuitry of the brick. The outlet provides alternating current, or AC power, which fluctuates back and forth. The first stage inside the brick uses components called rectifiers to force that chaotic AC wave into a steady, single-direction flow, known as DC power. Once the power is smoothed out into DC, it hits the primary control mechanism inside the charger, circuits known as DC to DC choppers. Wall voltage is far too high for a delicate lithium-ion battery. The chopper's job is to step that high voltage down to a manageable level that the phone can safely accept. Here is where the handshake dictates the terms. The phone's internal battery management system acts as the boss. It continuously checks its own chemistry, temperature, and current charge level and sends that exact data down the cable to the charger. The charger processes this data and responds by physically adjusting the output of its choppers, altering the voltage and current millisecond by millisecond. The charging brick has no agency of its own. It acts purely in obedience to the microdemands calculated by the phone's internal computer. Now we follow that precisely step-down electricity out of the brick, through the cable, and into the physical battery cells. This is where we hit the ultimate bottleneck of electrical physics, the equation P equals I squared times R. This dictates that the power transformed into heat equals the electrical current squared multiplied by the electrical resistance.
Because your phone's battery and the charging cable have natural internal resistance, forcing high electrical current through them generates heat. And because the current is squared in our equation, pushing just a little more energy generates extreme heat. Excessive internal heating degrades battery chemistry. Pushing past these thermal limits severely damages the lifespan of the device and introduces real safety risks. To defend against this, the phone's thermal sensors monitor the temperature. As things heat up, the phone instantly commands the charger to back off. The charger achieves this using pulse width modulation, or PWM. Instead of a steady stream, it chops the output into rapid, discrete pulses. By changing their width, making them shorter or spacing them apart, the system actively throttles real-time power without breaking the connection. Thermal physics, rather than the capacity of the components, governs the speed of your charge. To keep temperature safe, the entire system is forced to constantly pull its punches. This chart shows what that real-time negotiation looks like over a full 0 to 100% charging session. You'll notice it is a dynamic, shifting curve, not a flat line. Power output briefly peaks, but then continuously dips and tapers off. As the battery fills up and its internal temperature rises, the phone forces the charger to step down its output. Because of this constant thermal throttling, your device will only ever draw that maximum 65 watts for a tiny fraction of the total charging time, if it hits it at all. So when you plug in and see lower than expected wattage, the charger isn't underperforming. That fluctuating power reading is evidence of a closed-loop safety system functioning exactly as designed. Modern fast charging involves millions of rapid-fire data checks and voltage adjustments per minute. It carefully rides the thermal edge of physics, delivering exactly the right amount of energy your battery can handle at any given millisecond.